Have you ever really stopped to think about how a machine, just a bunch of wires and silicon, can actually remember something? How can it follow a set of instructions step by step without getting lost? Well, today we're going to dive deep into the fundamentals of digital memory and find out how we teach simple circuits to think.
It really all comes down to this one question. Think about a basic calculator. You punch in some numbers, it does the math, and boom, you get a result. It lives completely in the now. But then you have something like a traffic light. It has to follow a very specific sequence. Red, then green, then yellow, and back to red. It can't just pick one at random. And to do that, it absolutely has to remember which light was just on.
And that secret ingredient, the thing that gives a circuit a memory of the past so it can figure out the future, is a concept called state. You can think of state as a circuit's short-term memory. It's that little piece of info that tells the circuit exactly where it is in a process, which is how it knows what to do next.
All right, let's kick things off by talking about circuits with memory. We're going to look at what separates a circuit that just does simple math from one that can actually hold on to information. A leap that, honestly, makes all of modern computing possible.
Okay, so this slide really gets to the heart of it. On one side, you've got combinational circuits. Their output is just an immediate reaction to whatever you're feeding them right now. A calculator is the perfect example. You type 2 plus 2, it shows 4. It has zero memory of what you did 5 seconds ago. But on the other side, you have sequential circuits. Their output depends on what's happening now and on what happened before. That traffic light has to know it was just red to know that it's supposed to turn green next. It has a memory of its state.
So let's get a little more specific about what state actually is. It's basically a snapshot of the circuit's memory at any given instant. And that memory isn't just an abstract idea, it's physically stored in these tiny little hardware components called flip-flops. Just think of a flip-flop as a simple switch that can be set to either a 0 or a 1, and it'll stay that way until it gets a new instruction, effectively storing one single bit of history.
Now, when it comes to managing time, these circuits have two main flavors. Asynchronous circuits are kind of the wild ones. They react instantly the second an input changes. They are blazing fast, but designing them is an absolute nightmare because you have to predict every possible timing conflict. Synchronous circuits, on the other hand, are much more orderly. They use a master clock, kind of like a conductor in an orchestra, that tells all the little flip-flops exactly when to update, all at the same time. Everything happens in perfect lockstep. It might be a tiny bit slower, but it's way easier to design, which is why it's the foundation for pretty much all modern digital devices. And for our purposes today, we're definitely going to be focusing on these synchronous or clocked circuits. Okay, so before you can even think about building one of these circuits that can remember things, you need a plan, right? A blueprint. So let's take a look at how we actually model the flow of logic over time.
And our main tool for the job is this, the state diagram. It's actually a really elegant and powerful way to visualize what's going on. Each circle you see represents a possible state, a specific memory the circuit can be in. And the arrows? Those show how the circuit moves from one state to another based on the inputs it gets. It's basically a complete visual map of the circuit's brain.
Now, even within state diagrams, there are two main styles or models. A Moore machine is pretty straightforward. Its output is based only on the state it's currently in. So if it enters the green light state, the output is green. That's it. A Mealy machine, though, is a little more reactive. Its output depends on both its current state and the current inputs. For instance, it might be in a waiting state, but the output only becomes honk if it's in that state and it gets a car's presence signal at the same time. But, sometimes a basic state diagram just doesn't cut it. For the really complex stuff where you need more detail, engineers pull out the big guns. The algorithmic state machine chart, or ASM chart. You can think of it like a supercharged flow chart that gives you a much clearer blueprint for the actual hardware. It might look a little complicated, but an ASM chart is really just made of 3 simple building blocks. You've got the state box, which is a rectangle, and it just tells you what state you're in. Then there's the decision box, a diamond shape, which asks a question. It checks an input and sends you down one path or another. And finally, you have the conditional box, an oval, which is used for Mealy machines to show an output that happens during a transition, not just inside a state.
All right, let's switch gears. Imagine someone hands you a finished circuit, a total black box of logic gates and flip-flops, and your job is to figure out what on earth it does. This whole process is called analysis. It's like reverse engineering the logic. So that's the puzzle, right? We have the physical hardware in front of us, but we need to figure out its purpose, its behavior, its story.
We have to work backwards from the wires and gates to create that blueprint, that state diagram that tells us what it was designed to do.
And luckily, engineers have a very methodical way to do this. It's a three-step process. First, you literally trace the connections on the circuit diagram and write out the logic equations that describe what signals are going into the flip-flops. Second, you use those equations to build what's called a state table. It's just a big chart that says, okay, if I'm in this state and I get this input, I'm going to go to that next state and produce this output. And finally, you take all the data in that table and you draw the state diagram, which turns all that raw data into a map that you can actually understand at a glance.
Okay, now for my favorite part. Let's flip the script. Enough of taking things apart, let's build something new. This is the creative side of things, where we start with just an idea, a state diagram, and turn it into a real physical working circuit.
And you'll notice the design flow is basically the reverse of the analysis process we just talked about. You start with your cool idea, drawn out as a state diagram, and turn it into a formal state table. Next, you assign binary codes to your states. We'll talk more about that in a sec. From there, you figure out exactly what the flip-flops need to do by creating an excitation table. And finally, you use all that information to design the actual web of logic gates that will make it all happen. This step, state assignment, is absolutely critical. See, a flip-flop has no idea what red light state means. It only understands two things, 0 and 1. So we have to translate our human-friendly state names into binary. S0 might become 0, 0. S1 could be 0, 1. S2 is 1, 0, and so on. This is the moment we turn our abstract concept into the actual language of hardware.
And that leads us right to the excitation table, which is basically the instruction manual for our flip-flops. Think of it like this. The state table tells us where we want to go next. The excitation table tells us how to actually get there. It answers the key question. To go from the state I'm in now to the state I want to be in next, what exact signals do I need to send to my flip-flops on the next clock tick? This table is the final, crucial bridge between our grand plan and the physical logic.
All right, theory is great and all, but let's make this real. Let's see how all these concepts, states, diagrams, tables, the whole design flow, come together to build something that's actually useful. This is where the rubber meets the road.
So here's our mission, should we choose to accept it. We need to design a circuit that acts like a little digital detective. It's going to watch a continuous stream of zeros and ones flying by, and the very instant it sees 3 ones in a row, it has to raise a flag. And this is a super common task in everything from networking to data processing. So the first thing we have to do is think about what our circuit needs to remember. What are its states? Well, we can start with state S0, our reset state. We haven't seen any ones yet. If we get a 1, we move to state S1. Now we're remembering, okay, I've seen 1, 1. If the very next bit is also a 1, we move to S2, remembering I've seen 2 in a row. And if we see a third one, we go to state S3, which means success, I found it. And that's the state where our output signal finally goes high. Once we have our states defined like that, we just follow the recipe. We draw the state diagram that shows how inputs, the zeros and ones, move us between S0, S1, S2, and S3. Then we convert that drawing into a state table, then an excitation table, and from those tables we can derive the exact logic equations we need to build our final circuit.
And what do we get at the end of all that? The payoff. We started with a simple idea, find 3 ones in a row. And by defining states and following this methodical design process, we end up with a tangible, physical piece of hardware that does exactly that. It's a machine with a memory and a purpose, all born from pure logic.
And that really brings us to the big picture. This stuff isn't just an academic exercise. Right now, inside your phone's processor, inside the network routers that are bringing you this content, there are literally millions of these tiny sequential circuits. And they are all constantly on the lookout for specific patterns, command codes, data markers, network packet headers. So it makes you wonder, doesn't it? What other hidden sequences are being detected all around you, right now, just to make your digital world work?